Welcome to the lectures on modern digital communication techniques. So far we have discussed source coding, and after source coding we have been discussing about characterization of signals. We have described some ways to look at different kinds of signals, or how to categorize them in different ways, different forms. And then in the last few lectures we have discussed about how to represent these signals in a form so that they can be very general. And what we found out is generally if the signals are represented in form of exponential, weighted sum of exponentials, so which is usually represented through Fourier transforms, then you can handle things quite manageably. So in the previous couple of lectures we did discuss how to represent a signal, and we had taken a band pass narrowband signal. We had defined what is meant by that, and we had related the low pass equivalent signal representation to that of the band pass signal. So we had taken S of t as the real band pass signal, and then we have calculated SL of t. So that means if you would recall, we had S of t and we had connected it to SL of t through the relationships of e to the power of j 2 pi f c t multiplied by with SLT, as well as taking the real part of it. And we had also looked at how to represent the spectrum in the passband in terms of the low pass equivalent representation. So once having done that, then we said that this passband signal would pass through a band pass channel, and then we defined that the band pass channel in a similar form, where we said that the band pass channel would allow signals within its passband. So therefore the band should be around the center frequency of the carrier Fc, or Fc of the carrier would be around the band pass of the channel in that form. And then we established exactly a similar relationship, except the coefficient in front of it for the relating the passband equivalent passband of the representation of the channel with that of the low pass equivalent of the channel. Then we moved on and we said that, well, you have a passband signal which goes into a band pass channel, and definitely the signal that comes out of this would also be a band pass signal, and we call this R of t. So we connected R of t to correspondingly RL of t. RL of t is the low pass equivalent, and then we found that RL of t is connected, RT is connected to ST through convolution. Similarly, RLT is connected to the SLT with convolution with HL of t, which is the channel impulse response equivalent low pass representation. So having done so, we have the source, we have the channel, and then we started looking at instead of looking at signals, we looked at stochastic process. We said, what about narrowband stochastic process? We had started looking into it. Now why we are looking into such a thing? It's not arbitrary. The reason being, you have a source which generates signal, goes into the channel, right? We said in one of the early lectures at some point that channel is something which would change the source signal, right, in some form, which is usually like a filter. Like when you send something into a filter, it modifies the signal. And yes, in the previous lecture we have seen that the output of it could be R of f, or low pass equivalent is RL of f, is equal to the Fourier transform of the signal multiplied by the Fourier transform of the channel impulse response. So that means a multiplication in the frequency domain, and it's a convolution in the time domain. So that's what it does. It changes the signal as if there is a filtering process. Now then there is the receiver or the destination. So it's good to call this the transmitter, it's good to call this the receiver. Probably we have said before, or we can say now also, if you would look at the several receiver components, there will be filters, there will be oscillators, there will be low noise amplifiers, and so on and so forth, which would have several passive as well as active components. Now these components that are present would generally add noise into the system, and generally in one of the models, well accepted models, there is additive noise present in the system, right. And we briefly stated that noise is the realization of noise could be through a sample function, and which can be thought of as a band pass stochastic process, right? And of course, we'll talk more about it. So before actually studying noise, we'd like to study the characteristics of a band pass stochastic process, so that we have its equivalent representations and corresponding relationships between the time domain and frequency domain properties of it, so that when we analyze this system, we have modeled the signal here, we have modeled the channel, we have also modeled the output here. So once we are able to model this, then we will receive the signal at this point. Then our job would be to process this signal finally with the aim to reconstruct what was available at this point as closely as possible. So we've covered these parts. We are now in this particular section. So what we have done in the previous lecture was we had taken n of t as a sample function of a narrowband stochastic process, and we discussed about its correlation, and we invoked the stationarity condition. We said that let NT be a wide sense stationary process. Now, for a wide sense stationary process, we said that the typical thing that we know is the correlation function is dependent only on time lag and not dependent on the time. So that means if we say phi n of tau, where tau is the time lag, it's not a function of time, it's independent of time, but it is some function of tau. So going by that, we did arrive at a few relationships like phi xx of tau is equal to phi yy of tau, where x and y are the I and q components of the corresponding low pass equivalent quadratures of phi and t. That is what we said. So we also said that if zt, which is the complex envelope of nt, is represented as xt plus jyt, and phi is the expectation, phi xx is the expectation of x of t with x of t plus tau. That is what we said. And similarly phi yyt. So this is one of the relationships that we had, and we also had phi of yx of tau is equal to minus phi xy of tau. So these are the two conditions that we had established in the earlier discussion. And then since we also had the relationship that phi zz of tau is equal to phi xx of tau plus j phi yx of tau, and we could connect that phi n of tau is equal to real part of phi zz of tau e to the power of j 2 pi f c tau. So these are some of the relationships which we had established in the previous lecture, and this would help us, of course. So now what we will be interested in is, see here, if we look at things, we said that this is deterministic, this is deterministic, but since typical of these things are outcome of stochastic process, there is not much sense in actually taking the Fourier transform of these zt's or nt's. Rather, what we would be interested in are correlation properties and the power spectral densities, which are duals of each other in terms of Fourier transform. So what we will be studying is the power spectral density of this noise nt. So we will be getting phi n of f that we are going to get through the Fourier transform of the phi n of tau. So that means we will be directly writing it real part of phi zz of tau e to the power of j twice pi f c tau times e to the power of minus j 2 pi f tau d tau. So this is what we have with us. Now typical, this expression we have seen before, so we can straight ahead said that this is equal to half integral minus infinity to infinity, then bracket phi z tau e to the power of j plus phi z tau conjugate e to the power of minus j phi 2 pi f c tau. This is what we had been doing earlier, so it's not new for you, and we're going to get phi n of f is equal to, if phi z of tau has a Fourier transform of phi z of f, if this and this are Fourier transform pairs, so then what we have is this whole thing becomes this, right, where we can say phi z of f is the Fourier pair of phi z of tau. So this is the inverse Fourier, this is the Fourier relationship. So naturally this we have been using is of course phi z conjugate minus my f minus fc, right. So this is the expression again relating the autocorrelation of the band pass stochastic process to that of its equivalent low pass forms, where Z is the complex envelope of n. So this is the basic relationship which we have established. Now using this we will look at a few more properties of this noise process. So one of the important properties that we can try and see is that phi z of tau is equal to phi z minus tau conjugate, right. This will help us in arriving at some of the important things. So phi z of tau, this left hand side, is equal to half E is the expectation operator, Z conjugate of t, Z t plus tau, right, and phi z conjugate of tau would be simply conjugation of that, half E of Z of t plus Z conjugate of t plus tau. So we could change these things, and then if we would replace tau by minus tau, what we are going to get is phi z conjugate minus tau is equal to half E. So I'll write it here. So tau replaced by minus tau conjugate t minus tau z of t, and now we can say that let t minus tau be equal to alpha. So what we have is t is equal to alpha plus tau. So what we get is half E z conjugate of alpha times z alpha plus tau. So if you look at this expression and this expression, they are similar, and this is equal to this, right. The left hand side is this. Now we are seeing that the right hand side, which is this expression, is same as this expression in the left hand side. Therefore we can say clearly phi z tau is equal to phi z conjugate minus tau, right. So from this one can establish that phi z f is a real valued function. I would like you to recall when we did the Fourier relationships, we had if x of t is real, we said that x conjugate minus f is equal to x of f, right. That is what we had established. So now a similar thing applies over here. If this is true, then this is the dual in terms of the frequency domain or the Fourier transform. We get this result that phi z of f is real valued. So this is one of the important properties that we'll be using as we require. So now another small activity that we need here is any cross correlation function would satisfy the relationship that phi x y of minus tau is equal to phi y x of tau. So, this particular relationship one can try proving it, or otherwise we may fill this gap at some later time. So, we have these two things handy with us, and with this we can move forward, and we could also say that phi z z f is even function or even symmetric, right. So, we can look at that as well. So, we have seen this is real valued, we will just need to see that this is an even function. So, what we could check is phi z z of f is equal to minus infinity to infinity phi z z tau e to the power of minus j 2 pi f c tau t tau. This is by standard definition, right. So, since this is real valued, phi z z is real valued, we would go here, sorry, we have this thing. So, we could also go by that just a second, phi z z f is equal to phi z z tau. We could also say this is because of conjugate symmetry, we could say this is equal to minus infinity to infinity phi, sorry, what we need to do is at this point we will calculate phi z z minus f. This is what we are going to calculate, phi z z minus f, because for even symmetry we need to prove phi z z f is equal to phi z z minus f. So, minus infinity to infinity, this will be phi z z tau e to the power of j 2 pi f c tau. So, we have simply changed f to minus f, and this becomes plus d tau. At this point we would like to change over tau is equal to minus alpha. So, if we let tau is equal to minus alpha, minus alpha, d tau would be minus d alpha, and this range of integral would change from infinity to minus infinity. However, because of this minus, again the sign is going to reverse. So, you are going to get minus infinity to infinity, d tau can be replaced by d alpha, and there you are going to get phi z z of minus tau e to the power of minus j 2 pi f c tau is equal to this. So, through this we could establish that phi z z of f is equal to phi z z of minus f, that means it is an even symmetric function. So, now since we have established these few relationships, what we could further state is that since we have phi x y of minus tau is equal to phi y x of tau, this is one of the terms that we have. We also have phi x y of tau is equal to minus phi y x of tau. So, with these two relationships we could basically establish that phi x y of minus tau is equal to minus phi x y of tau. So, what this basically means is, if we would have this tau axis, phi x y of minus tau. So, if let us say phi x y at some value of tau, let us say tau 1 has a value here, and then I want to find, let this be phi x y of tau of minus tau. So, phi x y at let us say 1, 2, 3 some time interval, right. So, here I want to find it minus tau 1, phi x y at minus tau 1 is equal to minus phi x y of tau. So, basically you are going to phi x y of tau with a negative sign, going to go there, and if you let tau equals to 0, so you are going to get phi x y of 0 is equal to 0, which is basically should be equal to 0. So, that means if you look at this, it will be an odd function, phi x y is an odd function, right. It is an odd function, that is what we get, and for odd function what it would mean is that phi x y of 0 is equal to 0. right. So, that means that at 0 delay you are going to get no correlation between the x and y component. That means at tau equals to 0, x and y are uncorrelated. All right. But now please remember, this does not mean that x and y are always uncorrelated, that is for all tau. It is not necessarily true. So, but however, at this point let us make an assumption that for all tau x and y are uncorrelated, right. So, if we make this particular assumption that x and y are uncorrelated, what we get over here in this particular case is that x and y are quadrature components as well as they are uncorrelated. So, we will take this particular assumption and we will see what happens, so that helps us in characterizing noise finally, right. So, with this assumption that if on the assumption or this particular case, if for all tau they are uncorrelated, that means phi x y would be 0 for all tau. So, that means if they are uncorrelated, that means that is if phi x y for all tau is equal to 0, right. So, this in turn would mean phi z z of tau is real, right. So, if this is real, then this will be equal to phi x x of tau, right. It is not equal to phi x x of tau plus j phi y x of tau, and this would also help you in further proving that phi z z of f is equal to phi z z of minus f as well, right. So, we have this thing that phi z z of t is real only if this condition holds true. So, now in this case we take we are moving slowly into this noise. So, in the special case where so we consider the special case where the process NT, the stationary stochastic process, is Gaussian, right. We take this to be Gaussian, and that means x of t and y of t plus tau, we take this to be jointly Gaussian, right. We take to be jointly Gaussian, and that means they will be statistically independent. So, that means the PDF of such a function is given by p of x y equals to 1 by 2 pi sigma squared e to the power of minus x squared plus y squared by 2 sigma squared, where sigma squared is equal to phi x x of 0, which is equal to phi y y of 0, which is equal to phi n n of 0, right. So, once you have this, then we can use this further. So, what we now define is, or what we now go into is white noise. So, when we talk about white noise, it is a stochastic process. That means it is a process which produces values which are random, and they keep on changing with time. So, that is what definitely it is, and it is defined to have a flat spectrum, flat power spectrum, and call it a flat power spectral over the entire frequency range. Right, and so basically this condition would mean that you cannot express this in terms of quadrature components. So, what it means, we will not be able to express these in these terms, neither use these expressions. However, when we have done that, what we can say in typical communication system, your signal generally passes through a narrow band of frequencies, and if our signal is covering a band which is much smaller than that, and then we have, whereas originally noise was across this whole thing, but now if we say that it passes through a band pass filter, where the width of the filter is much wider than the width of the signal, in that case we have a white noise over the band of the signal, right. So, in that case we can treat the noise as band pass noise, right. That means the noise which has passed through a particular bandwidth. So, that means for such a case you would define phi n and f as, otherwise it was covering this entire band with a constant power, but now we say that it is covering only a particular band which is centered around f c, and let this band be B. So, similarly on this side, if we mark this as minus f c, is covering this band with this thing, and the value is n naught upon 2. So, this is the standard representation of band pass white noise, and what we are interested now is calculating phi z z of f, which is the equivalent low pass form of this, and clearly from this you can see that it is symmetric, and hence we can reconstruct the whole thing from this is 0 of course from one side, and we will use typically as we had done before that phi n plus, that means only the positive frequencies will take 2 u of f phi n n n of f, 2 because there are 2 on both sides, and u means we are going to take only the positive. So, this is one way of doing it. You could do it in another way, and then we would take phi z z of f as the translated one of this. So, phi n f plus f c. So, if you would do this, just see at phi z z of 0 is phi n plus, that means this thing at f c. So, that means it is now got translated, this is taking this frequency. So, if I would take phi z z f plus b by 2, that means here it will be b by 2 plus f c. So, that means now it is gone here. So, that means your phi z z is between here to here, which is b by 2, and also on the other side minus b by 2, right. And clearly this particular one would result in n naught, right. So, 2 times n naught by 2, 2 times n naught by 2 is going to n naught for the range of frequency f minus b by 2 less than equal to f plus f c, because this is only positive, less than f plus b by 2, right, f c plus b by 2. That means for f, so f plus f c, this particular set of frequencies in this range f c plus b by 2, f c plus b by 2 and f c minus b by 2, only in this range is this value equal to n naught, and otherwise it is equal to 0. So, if we now work on this equation, what we will get is for f lying between b by 2 and minus b by 2, this is equal to n naught. So, in other words, you can say that phi z z of f is equal to n naught for f less than or equal to b by 2 and 0 otherwise. Now, from this you could calculate the inverse Fourier transform, and you could get phi z z of tau, which is equal to, now this appears as this phi z z, and this is f, right. So, this will be n naught sin pi b tau upon pi b tau. Now, if in this one you let b tends to infinity, that means you would take this whole bandwidth of your consideration, then you would find phi z z of tau almost tends to n naught delta tau, and the power spectral density is symmetric as we are seeing. We have also seen that phi y of x of tau is equal to 0 for all tau. So, that would mean phi z z of tau is equal to phi x x of tau equals to phi y y of tau. So, with this what we complete is the relationship between the passband noise process, the autocorrelation function, and that of the phi n n n of f. So, that means yeah. So, we could relate phi n f to phi z z of f. That means given the power spectral density of the noise in the passband, we can also calculate its equivalent power spectral density at the baseband. So, using using all of this, what we have done in summary we have taken the frequency relationship of the passband and low pass equivalent of the signal of the channel and the output of this channel when excited by this, as well as the properties of stochastic band pass process, which we summarily say as noise. So, now we have but of course, for noise we have not talked about the Fourier transform of the sample function, but rather we have established the relationship of the autocorrelation function as well as the power spectral density. So, these particular set of expressions that we have developed are very critical, and we will be using them for establishing various receiver components and writing down expressions of transmitted signal in the rest of the course. We need to do one more important thing, that is the signal space and the Gram-Schmidt orthogonalization, which will give us a picture of the vector mode of viewing a signal. And then these, once we are through with these things, I think our representation or the way of unambiguous statement about a communication system will be easier. So, this particular part might appear to be a bit confusing, but a clear statement is you need to do these things by yourself a couple of times, so that you are used to this way of notation, and you can be confident of using this notation in all future setups that we handle. Thank you.